see me? Can you see me? I'm trying to record this podcast, but all the lights are out in my house. I have no electricity. So I'm using my knowledge of acids and bases to try and make a battery to run my whole house. Well, maybe this will help. Let's see. Can you see me now? Yeah, now you can see me. There I am. Yeah. This is all about titrations. What is a titration and so on. So let's go ahead and start it up. What is a titration after all? A titration is simply put using a known to help you find out an unknown, right? So for us, we're going to use a base that we know the concentration of and an acid that we don't know the concentration of. So we're going to use a known to figure out the unknown. That's the whole basis behind any titration. So here we see an acid that we don't know what the concentration is, and the base in the burette that we do know what the concentration is. And by adding base a little bit at a time to the acid, they will neutralize each other, and at some point it will form what we call a perfect neutralization, and we call that the end point. Now, how do you know when the end point is reached? Because you're making salt and water, so how are you supposed to know what it looks like? Well, that's when indicators come in play. These are indicators, and you have to pick it based on, well, which one do you want for a given task? Let's say that we're using an acid and a base where we know the end point is going to be somewhere around 4. We know that that's when the magical pH change will happen. And so would we pick, let's say litmus. Litmus doesn't change colors at 4. Would we pick alizarin yellow over here? No, it changes color way up around 11. So what could we use that has a color change somewhere around 4? Well, you might say thymol blue, but it changes color before it gets to 4. I think methyl yellow would probably be the best. We're going to use phenolphthalein because our endpoint is going to happen somewhere around the pH of 8. So we're going to use phenolphthalein, this one over here. And it's not white, it's colorless in acids, and it's kind of a fuchsia or magenta color in bases. We're going to add an indicator to the acid, and when we add base to it, it'll start out clear, and then at some magical moment, it'll turn slightly pink. Here's a video that tells you how to do an actual titration using the stuff in our lab.
Alright, let's start out with what is the purpose of a titration. If you needed to know how much of a given chemical is in a sample of river water, you could use a titration where you are using a chemical of known concentration to titrate it. In this podcast, we will be performing a titration to determine the molarity of a hydrochloric acid solution. In this experiment, you will need 2 50 milliliter burettes, a burette clamp and a ring stand, distilled water, 2 150 milliliter beakers, a 125 milliliter Erlenmeyer flask, a funnel, the phenolphthalein indicator, hydrochloric acid, and sodium hydroxide 0.1 molar, pipette, and a 10 milliliter graduated cylinder. Before beginning the titration, thoroughly rinse all of the glassware twice with tap water. Now rinse everything once with distilled water. Now take a burette and rinse 3 times with 5 milliliters of sodium hydroxide each time so that the solution can get into the tip of the burette. Do the same for the other burette, but use hydrochloric acid instead. Use the funnel to pour the sodium hydroxide solution into the burette. Do the same for the other burette with acid. Fill both burettes past the 0 mark. Then carefully drain the burette to the 0 mark. A graduated cylinder with 10 milliliters of hydrochloric acid, then pour it in the Erlenmeyer flask. Now add 2 to 4 drops of phenolphthalein indicator to the flask and swirl. Slowly add sodium hydroxide, 2 milliliters at a time, to the flask, and then swirl. You are looking for a light pink colored solution. If you got this color, you've added too much. To back titrate the solution, you have to add more acid. Slowly add HCl dropwise to the flask and swirl often. This is the color you should get when you've reached the equivalence point.
You've learned all about titrations, what they are, indicators. You've even seen somebody do a titration in lab. So all we have to do now is, how do you do the calculations for titrations? So let's get into it. MAVA, what's that? Well, MA, molarity of the acid. VA, volume of the acid. I know you figured out, therefore, that MB is molarity of the base and VB is volume of the base. But something doesn't look right. We need something. That helps, but doesn't really look like dimensional analysis, does it? Maybe this will help. Aha, much better. So what you can see now is we have a typical dimensional analysis problem. MAVA, when you multiply molarity times volume, what do you get? You get moles. So really, I could replace this right here with just moles of acid. All we're doing is solution stoichiometry. The molarity of the acid in moles per liter times the volume of the acid is equal to moles. And then this moles of B over moles of A, that's just so that units cancel. And where do those numbers come from? Well, from the balanced equation, just like in stoichiometry. And then that will be equal to MBVB, well, that's moles of base. All we're going to do is plug in the numbers we have and solve for it, doing the stoichiometry we've always done before. I'm going to give you another equation that's got the MAVA on the right-hand side and the MBVB on the left-hand side. I'm sure you're bright enough that you could do this yourself, but some of you may find it easier to have both equations, and therefore you know which one to plug into. So let me give you that. There it is. Is that ready? Almost. You're right. It needed the little bars, so it looks like dimensional analysis. All right, so get these in your notes, and let's go work an example. I got sulfuric acid. We're titrating it with NaOH, and I'm looking for the molarity of the acids. Let's see, which equation do I want? I think I want the one on the bottom. And the reason is, Ma right here. Yeah, I want that to be all by itself on one side so that I can solve. That's why I'm going to use that. You could totally plug in and use the top one. But for me, I'm feeling the bottom one right now. So let's do that. Go back to the problem. What do you always need whenever you're doing stoichiometry? Well, you need a balanced equation. Let's write one of those real quick because that's always fun. You got some NaOH. You're mixing it with some sulfuric acid. Now remember, that's a diprotic acid. So that's going to affect our balanced equation. So, and then we're going to make, because it's double replacement, some sodium sulfate and some water, agua, low, Wasser. All right, balanced, not so much. Maybe a 2 there, that'll look lovely, and a 2 there. Balanced, all right. So all we have to do is go back to the equation that I was using, the bottom one, and let's see, that was a molarity of the base. So that's 0.155 molar NaOH times the volume of the base. Now, technically, you should put that into liters. So I'm just going to go ahead and change that into liters, right? This is molarity. And remember, this is all of the NaOH. And we drew ourselves a line, maybe. So it looks like dimensional analysis, right? And then we said, let's see, it was moles of acid, I think that's what it said. So 1 mole of H2SO4. Now, where does the 1 come from? Well, it comes from the balanced equation up there. So just keep that in mind. And then on the bottom is moles of base. So it's 2 moles of NaOH. And that works out. Now my moles of base cancel, and I'm left with moles of acid. And if you remember, that bottom equation was molarity of the acid, okay, times the volume of the acid. The volume of the acid I know is 15.2. Oops, sorry about that. The volume of the acid, because it has to be in liters, my bad, was 0.0152 liters. Now all I have to do is do the math, and when I do the math, I can plug and chug and solve for molarity of the acid. I get, from the top equation up here, I'm going to get 0.0021219 moles of H2SO4. That's the left-hand side of the equal sign, is equal to the molarity of the acid times 0.0152 liters. And then when I do all the math, I get the molarity of the acid is equal to 0.1396. That's a 6. 0.197368 That's a really long number. I don't need all that. Sig figs. Looks like 3 seems to be the right number, so let's keep those 3. And let's cross out all that nastiness, and let's just go with 0.140 molar. And that's how you do the math. Pretty simple. Now, let's just think for a moment, what if the acid right here, what if this had been HCl? Well, if this had been HCl, then to balance it, you would just get rid of the 2's. The only thing that would change, besides the name of the acid, is this step right here in the middle. And that step right there in the middle is from the balanced equation, right? Other than that, all the numbers would stay the same. If I give you BaOH2, well, that's going to affect the balanced equation. If I give you phosphoric acid, that's a triprotic acid, that's going to affect the balanced equation. The only thing that should change in these equations is that part from the balanced equation. Make sure you have these in your notes, and we'll catch you in class.